The cosmos, a vast, intricate dance of starlight and shadow. For decades, we've watched galaxies spin, colossal pinwheels of stars and gas, each 100 billion suns strong. But here's the secret, the chilling whisper from the void. They spin too fast, so fast, they should tear themselves apart, fling their stars into the dark, desolate abyss. Our greatest minds, baffled, conjured an invisible scaffolding, a cosmic ghost called dark matter, a substance that interacts with nothing but gravity, holding these spinning behemoths together. It's elegant, it's pervasive, it's what our models demand. But what if that ghost is just a figment of our own limited understanding? What if the universe isn't missing anything at all, and instead, we've misunderstood gravity itself? All right, let's pull back the cosmic curtain on this grand deception. For decades, we thought we had the universe's mechanics locked down. Newton gave us gravity. Einstein refined it, showing us how space and time warp, how mass bends the very fabric of reality. It worked. It seemed to work. From apples falling to planets orbiting the sun, the math held. But then, the galaxies. Oh, the galaxies. Picture a colossal celestial merry-go-round, a swirling disk of stars. According to our pristine physics, the stars at the center, where most of the visible mass is concentrated, should be whipping around at blistering speeds. But as you move further out, to the edges of this cosmic pinwheel, the stars should slow down. Just like the outer planets in our solar system creep along compared to Mercury, right? It's basic orbital mechanics. More mass equals more gravity equals faster orbits. Less mass, less gravity, slower orbits. Simple, elegant, and utterly, catastrophically wrong. The first whispers of this cosmic discord came from the brilliant and tenacious astronomer Vera Rubin in the 1970s. She wasn't looking for missing matter. She was meticulously mapping the rotation speeds of stars within spiral galaxies, specifically Andromeda. What she found didn't just contradict our models, it screamed at them. The stars on the very fringes of these galaxies, where there's barely any visible light, where the gravitational pull from the visible galaxy should be weakest, were moving at almost the same speed as the stars much closer to the galactic core. Imagine trying to spin a pizza on your finger. The dough at the edge would fly off. But now imagine that pizza edge is somehow glued to the center, moving just as fast, defying every law of centrifugal force. That's what Rubin saw. These galaxies, by all rights, should have torn themselves apart, their outer stars flung into the intergalactic void like cosmic shrapnel. But they didn't. They held together. They spun with impossible cohesion. This wasn't a minor glitch. This was a gaping universe-sized hole in our understanding. To explain why these galaxies weren't disintegrating, there had to be an enormous amount of unseen mass, a gravitational anchor binding them together. We needed something more, and so we invented it. Dark matter, a substance that emits no light, absorbs no light, reflects no light. It doesn't interact with electromagnetism at all. It just sits there, an invisible gravitational giant, accounting for roughly 27% of the entire universe's mass, compared to the paltry 5% of all the normal visible matter we can detect. It was a stunning, almost desperate solution, a cosmic placeholder for everything we couldn't see, couldn't explain, but desperately needed to make the math work. But what if that placeholder isn't there at all? What if we've been chasing a phantom for half a century because we've refused to question the very rulebook of gravity itself? So, if dark matter is this invisible, omnipresent ghost, a cosmic band-aid for our broken math, what's the alternative? What if the universe isn't missing anything, but we're missing something fundamental about the rules of reality itself? Enter Mordechai Milgram. In 1983, this Israeli physicist looked at the problem of galactic rotation and had an audacious thought. What if gravity isn't constant? What if it changes its behavior when it's incredibly weak? He proposed a radical idea, a theory known as modified Newtonian dynamics, or MOND. Imagine a simple spring. You pull it a little, it resists a little. You pull it harder, it resists more. Linear, right? But what if, when you pull it barely at all, when the force is almost imperceptible, it suddenly stiffens, pulling back much harder than you'd expect? That's the essence of MOND. It suggests that below a certain incredibly tiny acceleration threshold, a threshold typical of the outer regions of galaxies, gravity stops behaving like Einstein's elegant curves or Newton's inverse squares. Instead, it gets a kick. It becomes stronger than our current theories predict. Think of it like this. Our engines of physics work perfectly at high speeds, describing the violent birth of stars or the fiery dance of black holes. But at the galactic equivalent of idling, at these incredibly low accelerations, the engine sputters, and our models stall. MOND says, no, the engine doesn't sputter. It just has a different, more powerful gear for those low speeds. And here's the magic. If gravity acts stronger at these minuscule accelerations, then those stars on the outer edges of galaxies, the ones that were spinning too fast and should have flown off, suddenly have all the gravitational pull they need. No invisible dark matter required. The visible matter in the galaxy, just by itself, generates enough modified gravity to keep everything bound. The flat rotation curves, the very puzzle that birthed dark matter, are explained by a tweak to gravity's rulebook, not by inventing a new, undetectable substance. It's a beautifully elegant solution, isn't it? Instead of adding a new, unseen component to the universe, MOND asks us to reconsider the most fundamental force we know. It shifts the burden of proof from, where is the dark matter, to, is our understanding of gravity complete? It's a profound shift in perspective. A cosmic detective turning their gaze from the suspect to the very laws of physics themselves. If you're finding this mind-bending, if your cosmic curiosity is tingling, hit that like button and subscribe. We're just getting started on this journey into the unknown. The scientific community, as you might imagine, didn't exactly roll out the red carpet for MOND. Imagine telling a room full of architects that the laws of physics they've used to build every skyscraper, every bridge, are fundamentally flawed when applied to, say, a feather slowly drifting to the ground. That's essentially what MOND proposed. Einstein's general relativity had been proven countless times, from the bending of starlight around the sun to the precise orbits of planets. It was the bedrock. To question it at such a fundamental level felt heretical to some. The initial reaction was skepticism, even outright dismissal. Dark matter had become the reigning paradigm, the accepted explanation, enshrined in textbooks and simulations. Billions of dollars have been poured into experiments designed to detect dark matter particles, massive underground detectors, particle accelerators smashing atoms to recreate the conditions of the early universe, even telescopes scanning the cosmos for its subtle gravitational whispers. To suggest that all of this effort might be chasing a ghost because the basic equation of gravity was incomplete felt like pulling the rug out from under an entire generation of physicists. But here's the thing about good science. It doesn't care about comfort or convenience. It cares about evidence. And MOND, despite its initial unpopularity, began to rack up some impressive wins. It wasn't just explaining the rotation curves of spiral galaxies. It was also remarkably successful at predicting the behavior of dwarf galaxies, those tiny, faint galactic companions that are notoriously dark matter dominated in standard cosmology. MOND seemed to fit their peculiar dynamics without any extra fudge factors. Then came the bullet cluster. This wasn't just two galaxies colliding. It was two galaxy clusters smashing into each other at incredible speeds. When astronomers observed this cosmic pileup, they used gravitational lensing, the bending of light by massive objects, to map where the mass was concentrated. According to standard dark matter theory, the dark matter should have passed straight through like ghosts, while the visible gas, slowed by friction, would have lagged behind. And that's exactly what they saw. The invisible mass was separated from the visible mass. This was hailed as the smoking gun for dark matter, undeniable proof of its existence. A crushing blow for MOND, right? Not so fast. Proponents of MOND quickly pointed out that while the bullet cluster is indeed a challenge, it's not necessarily a death blow. They argue that MOND, in its current form, is a phenomenological theory, meaning it describes what happens but doesn't yet have a deep underlying theoretical framework, like general relativity. There are extensions to MOND, relativistic MOND theories like TVS, tensor vector scalar gravity, that can explain the bullet cluster, albeit with their own complexities. It's like having a great recipe, but needing to figure out the exact chemical reactions that make it work. The debate intensified. Dark matter proponents pointed to the cosmic microwave background, the afterglow of the Big Bang, which seems to perfectly fit a universe dominated by dark matter and dark energy. MOND proponents countered by showing how their theory could explain the internal dynamics of individual galaxies far better than dark matter, which often requires tweaking the amount of dark matter per galaxy. The conflict isn't just about competing theories, it's a clash of philosophies. Is the universe full of stuff we can't see? Or are our fundamental laws incomplete? It's a cosmic chess match, played out in observatories and supercomputer simulations, with the very nature of reality as the prize. Each side has its strengths, each its weaknesses, and the universe, as always, holds its secrets close, waiting for us to truly understand its silent, spinning dance. So where does this leave us in the grand cosmic game of hide and seek? On one side, we have dark matter, the elegant and visible solution that perfectly explains the large-scale structure of the universe, from the clustering of galaxies to the ripples in the cosmic microwave background. It's the reigning champion, the default setting for almost every cosmological simulation. It provides a comprehensive framework, and the search for its constituent particles continues with immense resources. The simplicity of adding one more type of particle to the standard model of particle physics is appealing. It doesn't require us to rewrite the foundational equations of gravity that have served us so well. On the other side, we have MOND, the audacious challenger. It's a theory that, without invoking any new, unseen particles, precisely predicts the bizarre rotation of galaxies. It explains the relationship between a galaxy's visible mass and its rotation speed with remarkable accuracy, something dark matter models often struggle with without extensive fine-tuning. MOND offers a sense of completeness, suggesting that the missing mass isn't missing at all. It's just a misinterpretation of how gravity behaves at its weakest, most diffuse scales. It implies that the universe isn't full of mysterious interacting particles, but rather that our mathematical description of the fabric of space-time itself needs a slight yet profound adjustment. The tension between these two titans highlights a fundamental truth about scientific progress. Sometimes, the simplest explanation isn't the one that adds a new element, but the one that questions a long-held assumption. Is it more parsimonious to invent a new, undetectable form of matter, or to modify a law of physics that has only ever been tested in strong gravitational fields? Consider the implications. If dark matter exists, then our understanding of the universe's composition is largely correct, and we simply need to find the particles that constitute it. This would open up an entirely new branch of particle physics, leading to discoveries about the very building blocks of reality. It's a universe brimming with invisible potential. But if MOND is correct, the implications are even more staggering. It would mean that Einstein's general relativity, while brilliant and accurate in strong gravitational fields, like around black holes or within solar systems, is an incomplete description of gravity on the vast cosmic scales of galaxies. We would need a new, more comprehensive theory of gravity that seamlessly transitions between the Einsteinian regime and the Mondian regime. This would be a revolution, a paradigm shift on par with Newton giving way to Einstein. It would force us to rethink the very nature of space-time and its interaction with matter and energy. The scientific community is not stagnant. There's a growing movement to test MOND more rigorously, to push its boundaries, and to develop a fully relativistic version that can stand alongside general relativity. Experiments are being designed to look for subtle deviations in gravitational behavior at extremely low accelerations, deviations that MOND predicts, but general relativity does not. Space missions are being proposed to precisely map galactic structures and their gravitational fields with unprecedented accuracy. The debate is far from settled. Each new observation, each new simulation, adds another piece to this cosmic puzzle. For now, dark matter remains the dominant theory, largely because it provides a more complete cosmological picture, explaining not just galaxies, but also the early universe. But MOND, like a persistent rogue star, refuses to be ignored, offering a tantalizing alternative that challenges us to look beyond the obvious, to question the very foundations of our cosmic understanding. It's a battle not just for truth, but for the very nature of reality itself. And the universe, in its infinite wisdom, is waiting for us to figure it out. So we stand at a cosmic crossroads. On one path, an invisible ocean of dark matter, shaping galaxies with its unseen hand, a testament to the universe's hidden depths. On the other, a profound reevaluation of gravity itself, a whisper that the very rules we thought immutable bend and shift in the vast empty reaches between stars. Both possibilities are equally mind-bending, equally thrilling. One demands new particles, the other demands new physics. But the underlying question remains: how do these magnificent star cities hold themselves together? Is the universe a grand illusion where we've missed a colossal component? Or is it a subtle, intricate mechanism we've only begun to truly comprehend? This isn't just an academic debate, it's a quest for the ultimate truth about the cosmos we inhabit. It's the thrill of the chase, the agony of uncertainty, and the sheer exhilaration of discovery that drives us forward. Whether we ultimately find the elusive dark matter particle or rewrite the cosmic rulebook of gravity, one thing is certain: the universe will continue to surprise us, challenging our assumptions and expanding our minds. The mystery of galactic rotation is more than just a scientific puzzle. It's a profound reminder of how much we still have to learn about the reality we call home. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.